My name is Marilena. I will guide you through the rest of the evening. And yeah, we just saw the AI conversations. And if you use ChatGPT, you might see the sentence, longer thinking for a better answer. But yeah, even though the answer might not be better, what does thinking mean in that context? Can machines really think? That is the question now is targeted by Steffen Finck. He is the head of the Circular Lab here at the FHV University, and he brings together scientists, designers, engineers, so they can all think about how AI could responsibly contribute to a more sustainable future. And yeah, how does AI think? How does humans think? And what is maybe the difference between intelligence and autonomy? And also, what is about creativity and AI? That will now hopefully tell us Steffen Finck.
Thanks for the introduction. Yes, my name is Steffen Finck, and the title of my talk is Can Machines Think? So it has not a lot to do with circular economy. It's more about intelligence and artificial intelligence. And in the talk, I try to give a broad overview about what we consider as intelligent, what goes into intelligence, and how does this relate to artificial intelligence or the machines. And let us first start with intelligence. Intelligence is really, really difficult to define. So I have a background in engineering, and for us definitions are very nice because then we can concretely specify certain characteristics and properties. And intelligence is not very well defined. That makes also then the topic of artificial intelligence not very well defined, since if we don't know what's intelligence, then we also don't know what's artificial intelligence. And artificial intelligence or intelligence happens on several levels. So we have something like emotional intelligence, social intelligence, but also logistic or logic, reasoning, abstract thinking. People thought about some time about how to define intelligence, and the first definition of intelligence is the quote you see here. And it says it's the faculty of judgment, otherwise called good sense, practical sense, initiative, the faculty of adapting oneself to circumstances, and these are essential activities of intelligence. So it doesn't really specify what's intelligent. It just specifies how intelligence is observed by others, right? So it doesn't say intelligence is this or that. It just says, so if you are intelligent, you have those traits. This definition is from 1905. It's the first definition of intelligence, and it was developed by some person called Binet, and he was one of the first persons to develop actually intelligence testing. A much more interesting definition of intelligence is this one. So intelligence is a force. It acts to maximize the future freedom of action. It tries to keep options open with diversity of possible accessible futures. In short, intelligence doesn't like to get trapped. That's a completely different type of definition. It doesn't speak about good judgment or anything. It speaks about options and possibilities. And this one is from 2016. And there are many other forms of definitions of intelligence in between. And in 2007, Leck and Hutter looked at all those collections, at all those definitions of intelligence, and tried to A, summarize them, and then B, try to figure out a more universal definition of intelligence. So they looked at 70 definitions. 18 of them were already related to artificial intelligence. And what you see here in the word cloud is basically the most frequent traits or characteristics of intelligence that you can find inside those definitions. And you see it's very important to have reasoning, adaptability, learning, comprehension, understanding as important traits of intelligence. And they came up with a very broad definition of intelligence, namely stating intelligence is a measure of an agent's ability to achieve goals in a wide range of environment. So it's a very, very broad definition. It doesn't specify anything, but it doesn't necessarily relate to humans or non-humans or machine. It's just an agent, right? If we talk about intelligence, we also have to talk about cognition. In the preparation of this presentation, I thought about what's the difference? How do cognition and intelligence relate to each other? And I found this very nice metaphor where it says, so cognition is basically a car. The car is able to drive somewhere, it has the motor, it has the steering wheel, whatever. And intelligence is then our ability how to drive that car. So cognition is basically everything it's required. We have cognition sometimes in a conscious form, sometimes in an unconscious form. And intelligence is basically our ability or capability to use different forms of cognition. Cognition can happen in several ways, or there are several forms of cognition. There's something like perception, attention, memory, learning. We already saw learning as part of intelligence, abstract thinking, language, emotions, culture, and social. So it's also a very broad area where cognition happens, where cognition can appear. And the problem with cognition, at least from an engineering standpoint, is we can't really measure cognition in a direct way. It's really difficult to put an electrode or something in a human brain and then see what happens, and then also to interpret something like this, it's really difficult. So we have to do something else to figure out what forms of cognition are we using and how well are they developed. And we can do this with some kind of tests. There are a lot of behavioral tests for testing certain forms of cognition, and we can use some kind of pattern recognition, for example, to measure brain activities and then associate those brain activities with certain parts of cognition. But this is the measurement side, right? This is the empirical side. It doesn't really tell us something about how actually cognition happens. And if we understand what happens in case of cognition, then we might be able to infer how intelligence comes from that. And many people try different theories of how cognition happens. And some of those theories, I have some pictograms for them, are, for example, the information processing theory. The idea there is basically it works like a computer system. We have something like the connectionism that works like a network. So we have neurons, they're activated in certain forms of cognition and do these activations, input and information is processed, and we have certain types of visual sensors. We hear something, we read something like that. The next one is the embodied cognition. This is something also related what Margarita said before. That's the whole body. It's just not just the brain. It's the whole body. We have something like cognitive constructivism. The idea here is through learning we try to build an internal representation of our world, and then we use this internal representation to make our decisions. We have something more related also from the engineering system. That's like a dynamic systems theory or something like that. So this basically also applies to the idea that cognition and intelligence is not something static. It evolves over time. It evolves during having certain circumstances, certain external factors, and something like that. The last one is the free energy principle. Here the idea is that we have a certain type of free energy, And what we try is to minimize this free energy, which is equivalent to minimizing the surprise. So the idea of this form is to say, we don't like to get surprised, we like to stay in control, and this free energy model or this free energy theory tells us something how to minimize the surprise. And it actually involves a lot of different things. It's about the brain activity, but also the body, how is information processed. These are the theories we have developed for cognition in humans, and I'm not a neuroscientist, so probably some of those theories also apply to animals. But what we are more interested in, at least in this talk, is how can we transfer that to machines, right? The title of the talk was How Can Machine Think? And in this case, we can go very straightforward by saying cognition is nothing else than information processing. We have certain data, we have sensors where we can use or obtain those data. We put this data in some kind of processing method. This could be our machine learning systems, this could be some optimization systems, this could be some symbolic logic system, and then we are able to perform a task. And those ideas were used in 1956 to basically birth AI. So in 1956 there was a workshop at the Dartmouth College in the US, and this was the first time the term artificial intelligence was used. And the idea was there, if we can really understand and precisely describe how certain intelligent cognitive function in the human works, then we can apply them to machines and create machines that are able to simulate those features. Yeah? And since then, we're trying to do this. It had ups and downs of this development, but that was the basic idea. So it's not necessarily the systems we have today or we have 20 years ago. We actually, at the beginning, started out trying to build a system that is able to simulate a human, to do similar tasks like form abstractions, solve kinds of problems in terms of reading, mathematical problems, something like this. Now we come to the thinking machines. Again, if we have a complex problem, we try to simplify it. And the simplification in the thinking machines is that we like to define what this machine should do and how it should behave. And in the main work by Russell and Norvig, the idea was that the rational agent is the one that achieves the best outcome when there is certain uncertainty, or it tries to achieve at least the best outcome. Yeah. So in a nutshell, AI has focused on creating agents that try to do the right thing. But who defines what is the right thing? Right? At the moment, that's currently we or the developers of AI algorithms, but it's not always clear what is the right thing. Such agent can do a lot of things, a lot of different tasks. That's what we've seen today. So they can do search, they can reasoning, they can planning, dealing with uncertainty, decision making. We actually have certain approaches like an ant colony algorithm that is some kind of an optimization approach where basically this rational agent is an ant. Something also similar we have for the bees. But what is the rational behavior? So the street is empty, the traffic light is red. What do we do? What's the right and the rational decision? Do we cross the street? Do we wait until the light gets green? We have to define that in a certain way. Yeah? And how do we define it? How do we get machines to behave in such a situation? And how can we make machine do the right thing? I will not go into very technical details, but in some stuff you probably have heard before. The most promising approach so far, and I would say above 80% of all the AI systems that we have today, they rely on supervised learning. We have a huge training data set. We can train our algorithms on this training data set. For this training data set, we know what's the right answer. That's how we can train the algorithm. And then we have the model that achieves the task it should do. It could be a classification task. It could be a regression task. Most of the stuff. It could be something like, what's the next word in a sentence I like to generate? What is, at the moment, a little bit more promising for making the next jump in AI development is reinforcement learning. Here, I don't really want to learn an algorithm that predicts me something or forecasts me something. Here, I like to predict an agent that behaves in a certain way, that does this rational behavior. Here, I also need a lot of data, but what I need here is the agent needs to have some type of action it can perform, and I need to define some kind of a reward for this agent so that it says, oh, this was a good action, or this was a good behavior. Reinforcement learning is often associated with robot navigation, so that a robot can autonomously move around an uncertain environment. It's also often associated with game playing, because in reinforcement learning, we need a lot of simulated environments, because during the training of such an agent, a lot of stuff breaks. So because the agent runs against the wall, falls down a cliff, or something like that. And it's not possible to do that in a real world. Both of those are machine learning approaches. But we can do intelligent approaches also without doing machine learning, yeah? Because learning is always goal achieving. I would like to do some kind of skill acquisition, or I try to find the best solution I don't know yet. So one other approach is evolutionary computation. This is an optimization approach. I usually start here with some kind of a population. I evaluate this population. I do some kind of selection. I do some kind of variation to create a new population. This is analogous to the metaphor of evolution, right? This is how evolution works in its most simplest form. We have similar approaches for the ants, for the bees, for the grasshoppers, and almost for all animals that are out there, there is some kind of an evolutionary or a nature-inspired optimization approach. But also, standard classical optimization approaches can be creative and can be thinking machines. For example, if I would like to figure out the best route for a certain task, may it be the fastest route, may it be the route that saves the most fuel, or something like that, I can do that with classical optimization approach. The approach doesn't know the solution before. It finds a new solution. It gets creative to get a new solution. And we could also interpret this from a human way. We think a lot about this problem, and then we figure out what's the right solution. Just in this case, the machine does all the thinking. Where are we at the moment? I'm not sure how good you can see at the end, but we have a graphic. The dashed line is the human baseline, and all the colored lines are certain tasks we often associated with intelligence or cognition or certain abilities. Except for one line, that's for the multimodal understanding and reasoning line, all the machines beat the human baseline. So that means they have a performance that is better than the human baseline. It doesn't necessarily say they are better than humans, but at least the human baseline, they get better. And even for the last line, for this multimodal understanding and reasoning, the slope of the curve is really steep. So we could expect that in a couple of years, 2 or 3 years, we also, in this task, will beat the human baseline. So we have machines that can do the same stuff as we, maybe even better than us. Be it more faster, be it that they are more efficient. The problem is this one. As I said, most of those approaches rely on the supervised learning approach. And the supervised learning approach requires data. And I believe it's the Epoch AI research team estimated how much data do we have left. And with 80% confidence interval, they say data runs out between 2026, this is next year, and 2032. After that, we don't have any more new data we could use to train AI agents with new data, to make them more interesting, to make them better at something. And this is the problem why people now say the supervised learning approach comes to an end, and we need to do some kind of another approach to create the next wave of AI agents. And here, this type of reinforcement learning combined with robotics might be one way to go. At the end, I would like to speak a little bit about autonomy and creativity, since I promised I will do this. And we have a lot of examples for autonomous systems, right? We discussed, I think, in one of the, it was at either the presentation of the groups or before, whether we decide whether an agent is autonomous. This has ethics questions, this has moral questions, but we have already a lot of autonomous systems. Some examples are here self-driving cars. Yeah, they drive independently, there is no driver involved anymore. And for everybody who comes here, is here locally, I think this week or last week they said next year we have self-driving cabs in the east of Switzerland, so right across the border. So it's right in front of our door. Some other two examples. Salesforce launched this suite of autonomous agents for business operations, and traffic computer use is a possibility that this agent moves your mouse and all your parts of your computer to do autonomously certain processes, so it can complete tasks in real time. So you don't have to sit in front of the computer anymore. The agent will do that for you, answer your email, and everything else. But of course, autonomy has risks. We have certain ethical questions regarding decision making, who is responsible if something goes bad, who is liability. And of course, if you think about such an agent that is able to generate content, be it on a website, be it in social media, it can generate a lot of misinformation and distribute misinformation because the agent does not need to sleep anymore. Yeah? But let me make one thing clear. Just because content is AI generated doesn't mean it's misinformation. I think there's a same amount of misinformation by humans with intention. So we have to think about how to deal with agents and how to gather this coexistence between us and those thinking machines. And we have those three laws of robotics. These are don't harm humans, obey orders, protect yourself, and this is basically the balanced world. If we just change the order of those three rules, we either come to a frustrating world because it's too cold on Mars for the robot to go there and he doesn't like cold weather, or we have some kind of a killbot hellscape, which was, we have a lot of Terminator movies that actually deal with this topic. Yeah. Creativity also as part of autonomous systems about creating new stuff, finding new solutions, chartering the uncharted territory. It's really difficult because creativity is similar to intelligence, is very broad. It happens in different levels and different dimensions. But what we can do is to see how much of the chats or the talks with a certain chatbot happen and how much people actually work in this field. And what you can see here, most of the questions with Claude, this is a chatbot von Anthropic relate to computer and mathematical questions, but only about 3.4% of people work in this field. The next thing is arts, design, entertainment, sports, and media. 10% of all the conversations with Claude can be attributed to this area, but only 1.4% of the people in the US work in this field. So it's already used a lot for tasks where we have much less people working in those fields. And it's probably not a good thing for those people, who knows. We of course have also the other way around, right? So transportation and material moving, I'm not sure how many of you ask Claude or the ChatGPT how to move your sofa from A to B, but about 9% of the people work in this field. At the end, let me finish with two questions you might think about. So what we actually do is called anthropomorphism. So we give machines human traits because this allows us to better understand or describe what they are doing. But maybe we should ask, is this question, can machines think, actually the correct questions? Because we use the think here, it's a human trait. But machines don't really think, right? They just do some kind of optimization, they do some mathematical functions. It's nothing we would associate it with thinking. On the other hand, we don't really know how we as humans think. So this is unclear, right? But we also can turn the whole thing around. What would think machines about as humans? Thank you very much, and enjoy the following talks.